So this work is realized with Dominique Bertrand. So I am working in INRA, in the BIA unit located in Nantes. And in this unit there is a platform, BIPS. In this platform there is 4 components, and the new component is called phenochem. In this component we deal with chemotyping of polysaccharides and phenotyping of the internal structure of seed. For the chemotyping part, there is my colleague in the assistant, Sophie Legal, that you can meet in the room or close to his poster, to our poster number 9. So Dominique Bertrand is retired from INRA and is now a consultant in chemometrics in the company DataFrame. So this work is based on the following question: when harvesting? So it's possible, the possible answer can be when wheat is mature, when the kernel is well filled, or when the color of kernel is close to yellow gold, but the best answer is at the right time. However, the right time is not easy to determine and depends from some criteria like climate, cultivar, and we try to predict it, and to try to predict this right time, we develop a new system vision. So what changes occur during the maturity of kernel or wheat? There is some morphological changes like the grain growth or the grain filling, some molecular changes, and some changes related to the color, especially for the far red fluorescence related to the chlorophyll, or the blue-green fluorescence related to the hydroxycinamic acid. So the endosperm development can be divided into 5 phases. The first one is the formation of the first endosperm nucleus, and this is the list for the other one. And during these different phases, there is some changing, like the increasing in mass and in volume for the endosperm and the embryo. And what is interesting in this case, this is the degenerescence of maternal tissue from center to the outside of the kernel, and in the same time the enlargement of the endosperm. So the aim of this work is to develop a new methodology based on system vision to determine the physiological maturity of the wheat kernel. So how we can do that? We decided to use 8 wavelengths to characterize tissue. We choose 8 wavelengths because we think that not only one but a combination of the wavelength can discriminate some tissue from the others. So for the cultivar used in this work is the recital, and it was grown under controlled condition at the INRA of rain. So we choose 14 development time from 28 days after anthesis, and for each time we analyze 10 kernels. The step of sample preparation is fast and easy because the kernels were cross-sectioned at half length with a razor blade, because in this study the kernel at early stage development are not solid, and it's not. This is the only way to cut this kernel. Then these kernels are introduced in the multi-way imager. The multi-way imager is composed by a CCD color camera and 8 wavelengths. These wavelengths are issued from 3 spectral domains, 2 from the NIR, the near infrared, 3 for the visible, the red, green, blue, and 3 from the near UV, one at 360, the other of 370, and the last at 400 nanometers. So as we have 8 wavelengths, and as we have a CCD color camera, we have 8 lighting conditions and 3 RGB channels. So we obtain 24 plane images for each sample. So when you deal with only one wavelength, it's very easy. But when you deal with wavelength issue from different spectral domain, you have to adjust the exposure time. And for example, for the image acquired with UV light, we have to put the exposure time at 7 seconds. Whereas for the other light, it's less than 1 second, as you can see in this slide. So this is the result of an analysis, of a multispectral analysis of one sample. This is the 24 image obtained by the combination of the light and the RGB channel. So the three first image correspond to the illumination on infrared at 875 nanometers, and the channel red, the channel green, and the channel blue. So this is the algorithm. So once we have the different RGB image, we unfold all the image. We unfold all the image in a vector. So for the first image, we obtain the first vector, and we merge or concatenate all the vectors in a very large matrix. And in this matrix, the line corresponds to the pixel, and the column corresponds to the spectral response. So this large matrix is introduced in the principal component analysis algorithm, and we obtain scores, and we refold these scores in the initial dimension of the image, and we obtain a score image. As you can see here, the score image obtained from the PC1, the score image obtained for the PC2, PC3, and PC4. For this work, we only consider the score image issued from the PC1. And once you have the score image, it is easy to segment this image and to evaluate the number of pixels with a value, with a color. This color is the result of the PCA analysis, and this is an intensity value. And for example, if I segment at 0, I have all the pixels with the yellow-orange color to the dark red pixel. So the result now. Sorry for the quality, but you can see the RGB image illuminated with the UV at 360 nanometers. You can see some colors like blue, green, fluorescence, and you can see the evolution of the shape of the endosperm, the evolution of the colors, and the evolution of the different tissue. Like here you can see the maternal tissue or parenchymatous tissue, and you can see these degenerations and the enlargement of the endosperm. So we obtain the same image with the UV 400. And I don't know if you see, but there is a red fluorescence here, and around the endosperm. This image, like those previous, are classified with the days after anthesis. So, I present here the evolution of the image obtained from the PC analysis and the evolution of the image as a function of time. We can see the change that occur during the time, with the time, and the change of color. In the early stage of development, we had a lot of blue-green and yellow color, and at the final stage, we had a lot of red color and dark red color. So when we compare the result in the literature and the result obtained with the PCA, we can. It seems that our results are very relevant. Sorry. And if we segment all these images I presented previously, we can obtain the number of blue-green pixels, number of dark red pixels, or red pixel, or yellow pixel. So it is easy to follow and to monitor the evolution of the number of pixels. Here we can see here that the number of blue-green pixels is decreasing, and the number of red pixels and yellow are increasing during the same time. So to conclude, I think that I convince you that the memory system make it possible to quantify the degree of maturity of kernel. This is a summary of images. And the procedure for analyze, for cut the kernel, for acquire an image, and processing the image are about 3 minutes per sample. So this method is fast, simple, robust, and not expensive. To do that, we don't need to have human inspection, and we have no limit for image processing, but we have the limit of the sample presentation, which is the bottleneck of phenotyping in general. So with this method is possible to integrate in a robot, and it in this case, it will allow to increase the throughput of the analysis. In other work, we extract parameters like shape, color, or texture from multispectral images, which is very easy by using chemometric processing. So I thank you for your attention.